Alright, so today we're going to start chapter 13, which is the last chapter for this upcoming exam, which is gravitation. So here we're going to start looking at gravitation. Now, so far, when we talked about gravitation, or i.e. the weight of an object, or the force due to gravity, or the gravitational acceleration, we're only looking at a small section around the surface of the Earth. So if this was my Earth, basically what we talked about only exists for a very small region around the surface of the Earth. So in this region, the acceleration downward is approximately equal to g. Now, when I say approximately equal to, what I mean is there are other factors which take into account. So here, for it to be exactly 9.8 meters per second squared, that's assuming that the mass of the Earth is uniformly distributed throughout the entire Earth, which of course is not true. Also, geological factors, so things like iron or other places where there's a lot of densities, that causes it to be different. And the fact that the Earth is actually rotating, which we'll talk about in a second, with some angular velocity, also gives a different acceleration or local acceleration in every location. But again, on average, it's about 9.8 meters per second squared. So that's what we call the acceleration due to gravity. Now, again, this is only true in a small region around the surface of the Earth, but it turns out that if I start going further and further away from the surface of the Earth, the acceleration is going to change and actually get smaller. And it gets smaller because you're now moving further away from the system. So we then have to talk about gravity in its actual sense, as opposed to this approximate sense near the surface of the Earth. Now, when I say actual sense, what I mean is within the Newtonian dynamics that we're studying, not within the full-blown general relativity that Einstein came up with. But that's actually the more true gravity. But here we'll look at Newton's universal law of gravity. So, having said that, let's look at Newton's universal law of gravity. So what does Newton's universal law of gravity say? So it says if I have two masses, so let's say here's mass 1 with a mass of m1, and here's another mass m2 with a mass of m2. These two guys are gravitationally attracted to each other, and they're gravitationally attracted to each other along the line that connects the center of these two objects together. So if this is the center of the first, this is the center of the second, then the distance between these is r, so that's the center distance between them. And these guys are gravitationally attracted to each other such that this one is pulled in this direction, so this would be the gravitational force on 1 by 2. But on the second guy, this one's going to be attracted to him, again, along the direction of the line that connects the two. So this is going to be the force on 2 by 1. So these two are attracted to each other in opposite directions, but again, along the line that connects the two of these. Now, the magnitude of the force that each one of these guys feel is given as the force on 1 by 2 magnitude is equal to g, I'll tell you what g is in a second, it's capital G, times m1 times m2 divided by r squared. But simultaneously, the force on 2 by 1 is equal to g times m2 times m1 all divided by r squared. G is what's known as Newton's gravitational constant. So this thing is simply a constant. This is given as 6.673 times 10 to the minus 11, so it has units of Newtons meters squared per kilogram squared. Now, what's interesting about this then is that the force on 1 by 2 is actually exactly the same thing as the force on 2 by 1. Because here, if I simply switch the order of those two masses, since I can easily switch the order of two things and I still get the same number, for example, if I take 3 times 5, that's 15, or I take 5 times 3, that's still 15. So the magnitude of this guy is exactly equal to the magnitude of this guy, but they're in opposite directions. So this tells us then that the force on 2 by 1 is exactly equal to negative the force on 1 by 2. Which means that Newton's universal law of gravity actually satisfies Newton's third law. So For every action, there is an equal and opposite reaction, so these guys are attracted to each other with exactly the same amount of magnitude, just in opposite directions. Now again, since the masses are typically going to be different, that means the accelerations will be different, but again, the forces are exactly the same. So what does Newton's universal law of gravity tell us? What does it mean? So what it tells us is that any object which has a mass is gravitationally attracted to any other object which has a mass. So what does that mean? So that means I have a mass. My coffee cup here has a mass. The table has a mass. This controller has a mass. You have a mass. The Earth has a mass. So I am gravitationally attracted to my cup. My cup is gravitationally attracted to me. The force that we're being pulled towards each other is exactly the same. I'm being gravitationally attracted to the table. The table is being gravitationally attracted to me with exactly the same amount of force. Same thing with the controller. Same thing with you. I'm gravitationally attracted to you. You're gravitationally attracted to me with equal amounts of forces. And I'm also simultaneously gravitationally attracted to the Earth. Now, what this means then is I'm not being pulled towards you and you're not being pulled towards me, or my cup is not being pulled towards me and I'm not being pulled towards my cup, because what? The amount of mass that this thing has versus the amount of mass that I have are fairly small compared to that of the size of the Earth. Not to mention there's a static friction here and there's also a static friction between my feet, so I'm not seeing these guys being attracted to each other. So even though I'm being gravitationally attracted to everything, I'm not leaning in some direction towards my coffee cup, because ultimately the biggest thing around me is the Earth, which is why I'm being mostly gravitationally attracted to the Earth. So that's why I have most of me just being pulled straight down, not being pulled to the side. Now, of course, if I was in a vacuum, say in the vacuum of space, then yes, I would start to be accelerated towards this cup, because there would be nothing keeping me from being accelerated towards the cup. But again, at the same time, I'd be mostly gravitationally attracted to the biggest object, which in this case would be the Earth. So, this is Newton's universal law of gravity. So it just says that any two objects which have mass are simply attracted to each other, and they're attracted to each other in a way that is proportional to the product of the masses divided by the distance between them squared. So the closer these guys get to each other, the smaller this number is going to become, which means the bigger that the force is going to become. Now, since the force is becoming bigger, that means then is, of course, the acceleration is going to become bigger, so the acceleration between them would actually get bigger as well. So these two objects would start moving with small acceleration until they got closer, then they would start speeding up, and then eventually collide with each other. So, this is Newton's universal law of gravity. Now, what happens if I have the first scenario we're talking about? So there's me, and there's the cup, and there's the controller, there's the table, there's the Earth. So how do I determine then the net force on, say, me from all of these other massive objects? Well, it turns out that Newton's universal law of gravity satisfies what's known as the superposition principle. Now, superposition principle is just a fancy way of saying that the net force acting on an object is simply the vector sum of all possible forces acting on that object. So let's say I have a whole bunch of objects. So here's mass 1, here's mass 2, here's mass 3, here's mass 4, and let's say this is the mass that I'm interested in, let's say mass 6. Now, each one of these guys is separated by distance, so let's call this one R16, call this R26, call this distance R36, and this distance then is going to be R46. I don't know why I skipped 5, but whatever, that's fine. Now, again, what's going to happen then is that M6 is going to be pulled towards all of these different masses. So that means that in this direction, it's going to feel a force of F16. In this direction, it's going to feel a force of F26. In this direction, it's going to feel a force of F46. In this direction, it's going to feel a force of F36. So that means then that the total force on this object is simply going to be the vector sum out of all of these, which means it's going to point in the direction of the net force. So depending on the size of these things, I don't know, let's say it's going to be down in this direction. So ultimately, F6 is going to point in this direction. So we then say that the force on 6 then is going to be equal to the force on 6 by 1 plus the force on 6 by 2 plus the force on 6 by 3 plus the force on 6 by 4. Or in summation notation, this is then the same thing as the sum over I of then F6I. So these are all the different forces acting on him. Now, using the universal law of gravity, we can then rewrite this then as G times M6 times then the sum over I of Mi over R6I squared. So this then would be the net force acting on this object, and this all points in some particular direction, so this would be in the R6I hat direction. Now, again, gravity is actually attractive, so here we need a negative sign due to the fact that the attractive force means that they're always pulled in the direction opposite to these two guys. Now, so this is what we call the superposition principle. Superposition principle. So again, it just means that if I have a collection of particles, then in this case, the net force on one of those particles then will be simply equal to the sum over all the individual forces between that particle and all the other particles, vector summed together, to give the final net result. So this is what we just call the superposition principle. But again, it's just a fancy way of saying that this is the net vector force acting on an object. Now, this is true if I have a collection of point charges, or point masses here, all pulling on this guy. But what happens if I have a continuous object? So meaning that, what if I smash all of these other masses together into one big collective mass, and then I'm looking at the mass on, or the force on this guy. So let's say here, this is my big mass, called that capital M, and this is my little mass M that I want to know the force onto. Well, basically the way we do this is the way we've done pretty much everything, is we're going to take this big mass and we're going to chop it up into a whole bunch of small pieces. So meaning that I'm going to take this thing and I'm going to chop it up into a small mass here, let's call that delta M1. Another mass here, let's call that delta M2. Another mass here, let's call that delta M3, and etc. So each one of these guys then is some distance away. So this one is going to be R1, this is going to be R2, this is going to be R3. And again, what we know is that gravity is an attractive force, which means that along the line connecting these two masses, so force 1 will point off in this direction, force 2, make sure I draw that correctly, good, is here, so F2 would be this way, and then finally F3 would be this way. So again, I would vector sum all these guys together so that the net force acting onto my mass here would be in the direction of the vector sum of all those, so this would be the net force on M. So, again, using our superposition principle, all this thing says then is that what? I'm going to basically just copy this, that the magnitude of the net force on M then is equal to G times that mass of M times then the sum of these delta MI's divided by RI squared. This would be the magnitude of the net force. Now, what we typically do then is I want to turn this from a cutting up into large objects into cutting up into infinitesimal objects, which basically means I'm going to take the limit as all of these delta mi's goes to 0. So in this case, we're going to then take the limit delta mi goes to 0 of then g times m times the sum over I again delta mi over ri squared. And as we talked about before, the limit of an sum, in this case, is then the limit of an infinite sum, means that this thing turns out to be an integral. So then I get g times m, where again m is the mass of the body that I'm interested in, times the integral then of dm, all divided by r squared. So what does this mean? So again, this means I'm simply going to take this thing and I'm going to chop it up into a bunch of small pieces, where again, each one of these pieces is going to have some sort of differential mass. So here, this is going to be my dm. So r here is then going to be the distance from, here different colors here, is going to be the distance from dm to the actual object. So this is my distance r. So again, theoretically, all I'm doing is I'm taking this object, chopping it up into an infinite number of pieces, where each one of these pieces has a differential mass of dm, and then r is the distance from that's dm to the point of interest, which is the actual mass that I'm trying to determine its force. Then from here, I'm going to sum all those together. I am simply going to do an integral. In that case, then take the gravitational constant times the mass of the object, and then add as the net force onto that object. Now, we talked about this before when we talked about moments of inertia, but again, to integrate over a mass is kind of a useless type statement. It's kind of a strange statement. So again, typically what we're going to do is exactly what we did then, where we're going to turn this dm into a geometry integral instead of a dm integral. So integral over the mass. So again, depending on the type of symmetry that we have, dm then will either become lambda times dl, eta dA, or rho dv, then depending on what type of geometry that the system has. But again, anytime I'm dealing with some sort of continuous distribution, so this would be a continuous mass distribution. In that case, then we have to integrate over the geometry of the mass distribution instead of just using the simple superposition principle. But again, I can use this guy. I can use this guy then when I have discrete masses, and then I can use it also when I have a collection of these discrete masses. Now, one of the most interesting things that Newton's universal law of gravity tells us is that if I have a massive object, say something like this, and I am outside of that massive object, so this is the mass, this is my mass, this is me, and I'm looking at this massive object, from the outside, what I only see is the fact that all of this thing, which has a total mass of, say, capital M, all of that mass seems to be concentrated at a given point. So it's not fully distributed, so basically means that if I'm looking at a massive object, say such as the Earth, gravitationally speaking, it acts as if all of that mass is concentrated at a single point. So from the outside, this massive object acts just like a point mass. Now, if I had a regular shaped object such as this, like the sphere or the Earth itself, it turns out that that point at which all the mass seems to be concentrated is at its geometric center, which in this case would be right here. So meaning, if I'm sitting out here, gravitationally speaking, I'm attracted to the center of mass of this object, which would be at its geometric center. So even though this thing has mass uniformly distributed throughout the entire thing, it acts as if all of its mass is concentrated at this point. Now, why that's interesting is because let's say I actually start to fall, and I'm going to start falling into the object itself. So let's say I follow this path, I'm going to follow it all the way down to its center. So what's interesting about this is as I'm falling, anywhere where I'm on the outside, I'm still seeing that I'm attracted to this thing with a force, whose magnitude is simply equal to g times the mass of that object times my mass divided by the distance r squared. So anywhere on the outside, this is true. But as soon as I start falling on the inside, what interestingly happens is once I get onto the inside, let's say I'm sitting here, I don't care about the mass on the outside of me anymore. What I only care about is the mass which is inside of an instantaneous sphere of this radius. Let's call this, I don't know, x, just for now, since I already used r here. So whatever this distance is, whatever this instantaneous sphere is, I'm only attracted to this mass on the inside, not the mass on the outside. So imagine that as I'm falling in, this thing is made out of, it's like an onion. It's made out of layers. So as soon as I pass through one of these layers, that layer then comes off from the outside, which means that effectively the mass of the object is getting smaller as I fall on the inside of it. So when I'm on this portion here, what I care about is only the mass which is included inside of this instantaneous sphere, which is then going to be the effective mass. So again, what's happening is as I fall inside of this thing, I'm imagining that as I fall in, all the mass then is actually coming off of the outside, stripping away, so what I'm seeing, gravitationally anyways, is that the mass is actually getting smaller. Until I reach all the way down to the geometric center, where now there is no more mass. So what actually happened is, as I'm actually falling through, the effective mass that I'm seeing, again, gravitationally speaking, is getting smaller and smaller and smaller and smaller, until eventually I get to the center of the object, in which case I feel no force because there is no mass, until eventually I'm going to come out through the other side. Now as I'm moving through, this effective volume is getting bigger and bigger and bigger, which means the force is getting bigger and bigger and bigger and bigger, which means the acceleration is getting bigger and bigger and bigger, until eventually I'm going to reach to the outside again, at which time I'm going to see the total mass of the object, so I feel then the total force. So ultimately what this means is, let's say if I took the Earth, and I cut a hole through the center of the Earth, so here is my hole, and then I took a mass here of mass m and I let it fall through, what's going to happen then is that this thing is actually going to harmonically oscillate back and forth. So what will happen is it's going to feel the maximum amount of force here, means it has the maximum amount of acceleration, but then as it falls through, that acceleration gets smaller and smaller and smaller and smaller until I reach the center point, at which point in time the acceleration will become 0, so out here I have a max. Then as it moves through, the acceleration gets bigger and bigger and bigger, just in the opposite direction. So here the acceleration is pointing downward. So as it moves through here, the acceleration is going to reach, again, a maximum acceleration at this point. It would just now be in the opposite direction. So meaning that if there was vacuum through here, so there was no air resistance or anything, as I drop this mass, it's simply going to harmonically oscillate back and forth between the outside of the Earth on both sides. And it's going to do this with some sort of period which we could actually calculate, but we're not going to worry about that right now. But just note that as this thing falls through, what happens then is, again, the Earth itself would act like an onion, at least gravitationally as far as we're concerned. So as soon as we pass through a layer of the onion, that onion layer would come off, and we'd only care about the mass that's left. So every time we pass through a layer, the mass is going to get smaller and smaller and smaller, until eventually we get to the center, where there would be no mass. So in that case, we would feel 0 gravitational force at that particular moment. Now again, here I'm assuming that the mass density of the Earth is a constant, which, again, as we talked about at the beginning, we know that's not actually true, but again, more in a theoretical type sense. Now this is what's known as Gauss's law. So it comes from the fact that we have a divergence. We're going to see this again in 206 when we start talking about electricity, when we come back to Gauss's law. So that's mostly what I'm bringing it up now, to kind of give you exposure to it when you actually see it again in 206. So that way you're not completely shocked by this thing coming out of nowhere. But again, just know that this is true. Now, as I mentioned, when it comes to things like the Earth is actually rotating, which means that the acceleration due to gravity is actually going to be changed due to the fact that the Earth is actually rotating. So again, if I look at the Earth here, so here's the Earth, here's our rotation axis, so that this is, say, the North Pole and this is the South Pole. Even though the magnetic poles are slightly different than the rotation poles, but let's not worry too much about that right now. But again, we know that this thing is actually rotating. Well, since this is rotating, what's going to happen then is we're also going to pick up a centripetal acceleration. So if I was, say, standing here on the surface of the Earth, so this is me, but since I'm rotating, that means I have a rotational speed then tangentially into the board at this point, so this is my tangential velocity, and I'm actually rotating about a circle whose radius is defined by this radius. So this is going to be my radius. And then this is the equator, so this is then the latitude, so this is my latitude angle. So this is my latitude angle. So basically what's going to happen then is I'm not only going to feel the acceleration due to gravity towards the center of the Earth, so I'm not only going to feel this AG towards the center, so this is my acceleration due to gravity this way, but I'm also going to have a centripetal acceleration towards the center of the Earth. So this is going to be my radial acceleration in this direction, which which means that the total local gravity that I feel at this point is actually going to be the vector sum of these two things. So that means the total gravity that I'm going to feel is actually going to be off in this direction. So when I say that I have a local gravity, where local gravity would be in the direction of, say, my keys, my plumb bob. So in this case, if I was holding out my keys and I said this is the direction of G, because my keys are being pulled in this direction, I have to note that this is actually the vector sum of the acceleration due to gravity due to the fact that the Earth is massive and my keys are massive, and the fact that I'm actually moving in a circle, so there's a centripetal acceleration, which is causing a slight deflection. So anytime that I'm looking at my keys that determine the direction of the acceleration due to gravity, it's actually the vector sum of these two objects. So the total acceleration that I feel at this stage will be that gravitational acceleration plus then the radial acceleration towards the center. So this is going to have the greatest effect when I'm at the poles. Or not at the poles, but at the equator. So when I'm at the equator, then the acceleration due to gravity will be towards the center of the Earth, so this would be G. That centripetal acceleration will also be towards the center, which means that these two summed together would give me in total local acceleration G, which would point towards the center, which would give me a larger acceleration on the poles, or sorry, on the equator, than it would, say, at the poles, because at the poles, when you're sitting up here, you're not rotating at all, which means that you have no centripetal acceleration, so you're only feeling acceleration towards the center of the Earth. So whenever this thing is actually rotating, we also have to take into effect that this thing has a centripetal acceleration towards the center as well, which is actually going to cause the local gravity to be different. Now, the overall effect that this thing has is this is actually what causes the Earth to get squashed more into an ellipse as opposed to a perfect circle. And the reason for that is, again, as I'm actually moving across this line, it has the greatest effect here. So what happens then is what? There's zero effect here, greatest effect here. So as it's moving through, what actually happens is it kind of flattens out this portion of the Earth, causing the bulge more out in the equatorial line, and then, again, kind of flatten out and be pushed inward then a little bit for the poles. But, again, so just note, again, as I'm standing here, the direction at which my line is pointing isn't in the direction of just the acceleration due to the fact that this has mass and the Earth has mass. It's actually being slightly pulled to the side due to the fact that we are rotating about in a circle, where that circle is defined by the radius at which we are latitude-wise, which then gives us a centripetal acceleration towards the center. So next time we'll start looking at some examples of these things and see how they actually work.